Uh, Hi guys, my name is Gennady Fedorov. I'm technical consulting engineer and represent here the Intel Performance Libraries team. And today I will talk about, I will provide only very short overview of what we have with performance libraries, our latest update, and might be will show some examples on dev cloud systems to show how MKL examples works there. Yeah, and like this is very this was already you could see you saw this was many times today. This is just one API based toolkit contained content just into this content there are many performance libraries, which one of them is well known Intel Math kernel library, oneAPI Math kernel library, which called oneMKL, one Intel oneAPI data analytic library, Intel integrated performance primitive, and deep neural networks library. But today, just because of the time, we have some time constraint, I will provide a very brief overview for Intel MKL Data Analytics Acceleration Library and Intel Integrated Performance Primitive. DNN discussion with DNN might be delivered into the separate sessions the next time. And just his very short agenda for today. First of all, I'm gonna speak about MKL, then about our performance primitives, and the last topics would be about data analytics acceleration library. Well-known library, oneMKL, just to remind you that MKL provides C and Fortran API for a very long time. And since the last year, since the previous version of MKL, which is 2021, MKL suggests customer DPC++ interfaces as well, which is main topic for today to speak about and to show how it probably works on your side, on our side. Intel MKL just provides cross-platform interfaces, and Netlib, BLAS, and LAPEC interfaces are so-called base standard interfaces, which support by all math libraries around the world. And MKL has supported exactly the same interfaces, and plus some so-called extension, MKL extension, which are not part of standard Netlib interfaces as well. We are just aligned with the latest Netlib version 3.9 and align from version to version of MKL. We align to the next version of Netlib as well. Of course, MKL supports Windows, macOS and Linux operation systems, 32 and 64 bits implementation of these libraries, of these interfaces. All our libraries, all our routines from MKL are highly intensive, optimized for all available Intel architecture, and it could be done. And when the code running on the code on the some specific hardware, customers don't need to choose which library could be linking against, and it could be done automatically when the code could be running on this specific hardware, and the most optimized code branch could be running, could be loaded and execution further without customer extensions. In the case if customers would like to see how this code would be to compare which hardware branch, the performance of hardware branch, for example, with AVX2 against AVX5 code, there are some routines and environment variables which could allow users to choose this specific code branch to run this code and to compare the final performance. And MKL supports different OpenMP threading building block runtime and and MPI runtime as well. Today, just we could see at this files that we could see that MKL contains linear algebra, basic linear algebra blocks, LAPACK, scale pack, sparse solvers, sparse plus, direct and distributed sparse solvers, and fast Fourier transformation for 1, 2, 3, and 7 dimension contains all optimization regarding to this dimension with different types of modes of computations, in place, out of place, complex to complex, real to complex, and further. And a wide set of random number generators, including distribution and many of types of generators. Some set of summary statistic you might see here as a list of these functions. Very wide set of vector math libraries which just to compute when the vector inputs. The inputs vectors are pretty long, makes sense to run MKL code there, and it will give you the it will give you a lot of performance benefits compared with the same functionality which is available from Intel compiler as well. And a lot of another functionality we have one-dimensional splines and interpolation trust region functionality at further. All of this functionality available with C and Fortran interfaces, the same. But here, just since MKL 2021, which this product, this version has been released 1 year ago, we just extend this functionality to with DPC++ interfaces and all of this. The most important part of MKL functionality available to run on GPU, Intel GPU at this moment, and you could see solid red lines. There's all most important BLAS functions available to run on GPU side. Some of all functions from fast Fourier transformation. Only recently in the latest 2022 version of MKL, we added our FFTW interface opportunity to offload on GPU side as well. And with random number generators, only the most important types of generators and distribution mode available to run on GPU side as well. If you are talking about vector math libraries, everything available to run on GPU, on CPU side, with DPC++ interfaces, with C and Fortran interfaces, as well. Another part of our functionality, like solvers, outside of our if are available on CPU and CPU part only, and they continue to support only C and Fortran interfaces, and not available to run on GPU side. And this is very general, very general description of what we exactly have. Because of MKL support, you could spend a lot of time to explain the difference between buffer and shared memory approach. MKL contains USM contains DPC++ interfaces for shared for USM and for buffer interfaces both. MKL contains a C and Fortran openapi offload mode. And you might see here from this table all BLAS and the most important BLAS extension like batch modes are available to run on GPU with in offloading mode, with DPC++, USM and buffer interfaces both, and of course with traditional to run on CPU side. On CPU side, in this case, we could speak about host, for example. If the code contains DPC++ API, they could compile and execute it on host, for example, on CPU or just GPU side. If you're talking about LAPAC and LAPAC-like extension, you might see that not everything available to run on GPU side because of we selected only most significant part of typical LAPAC functionality like eigenvalues, eigenvalues computation, solution system of linear equations, and ported these examples, ported these routines to GPU with DPC++ interfaces. And just that's mean if you look at the developer reference or header files, you might see the list of functions where this list is pretty wide, but not everything cover LAPAC functionality. You need to let us know if you like to see those some of functionality which we don't support at this moment. All cluster companies like ScalaPack, like cluster FFT and sparse solvers are not available to run on GPU at this moment. We just only might be thinking about how and when we could do add this functionality further, but not at this moment. At this moment, we don't support. As I already said about vector math libraries, everything, every modes with vML functions available to run on GPU and CPU with different interfaces, with different with oneAPI offloading, with C and oneAPI interfaces as well. Okay, regarding to fast Fourier transformation, here just we added only recently one update ago that FFTW interfaces are just available to make some C and Fortran offloading offloading to the GPU side. That's all I would like to speak about right now. Here, just I wanted to show you. It's not demo. This is short examples from a matrix typical C interface for matrix multiplication. How you need how efforts you need to do to port the existing code to the DPC++ interfaces. This is just kind of examples, very trivial examples, of course. The main idea to allocate all free buffers for working matrices and to call initializing stage has been skipped for brevity, and then you could call standard C+ DGEM API. The API is traditional, the same API supported by NetLib, etc. Nothing new in this case, I would say. But what we need to do to how we could optimize this code to offload this code to the GPU side. You may add only here a couple of lines of the code, of course, to just to map arrays which we need to offload to the card and get back. In this case, all arrays A, B, and C could be offloaded to the GPU from the host, and then matrix output results could be back. And only in the next line of this code could be just use target variants to dispatch the requested GPU to execute DGEM, in this case DGEM functions on this GPU side. Of course, we could use here. We used shared memory allocation, USM pointers, and we could add here no wait clause to make to think about asynchronous execution. Igor spent essential time to provide to describe the behavior. Using no wait, it's up to you. It depends on your workflow into your implementation. And if GPU could be find out, then this code could be executed on GPU side. That's all. That's all you need to modify the code. Of course, the linking stage, and I will show build how to build this code, because of building process is significantly different compared with so-called classical C and Fortran interfaces. And the next foil, this is how DPC++ interfaces looks like. The same code, but code not offloading, but how USM unified shared memory interfaces BLAS looks like. And you might see just we edit only namespace, open oneAPI MKL namespace, adding here. Then we create traditionally setup CPU queue or CPU queue, sorry, and allocate memory. The same initialization could be done as well, and code could be the API could looks as follows. Here also there are some another the last parameters is so-called dependencies, but it's you could skip these parameters because of its optional parameters. You could see that the differences between API are very similar, like with similar with netlib API. The first parameter only Q, and might be the last parameter could be added. It's not it's for BLAS level 1, for example, the API slightly there are some additional differences because of you might remember in BLAS level 1 we routines return the output output results to the output results. For DPC++ interfaces, the output results could be added as a last parameters. But in general, the interfaces are very similar, and it's pretty easy to modify your code to make it run to the GPU side, to make it run on GPU side. Let me then show you the live examples, just which I prepared. Microsoft. I will show. I will try to show DevCloud system where I prepared some. This example. Do you see my screen at this moment? I shared DevCloud system.
Yep. Yeah.
Okay. Let me. Okay, I just here I prepared and already compiled two examples with buffer and shared memory interfaces, just to let you know that the performance for both of these interfaces are very similar, not exactly the same, but very similar. I will run to very ceiling for on very not very power graphics card here. We could see here only 12 units, but and compare the results against host performance. Let me first of all to show how this example looks like the GEM just not interested part. As I show, as you saw at the foils, just the code is pretty trivial. Just we just for brevity, for simplicity, I used here the square matrices. Just doesn't matter. The behavior would be the same. Might be it depends on performance, but the general idea here to show how to call, how to run, and to see the performance benefits you could have. And we could create, of course, create contents, context, then create queue, of course, allocate here memory just for all working arrays, just some kind of initialization by but arbitrary numbers, and then just we create all and measure the performance. We could use weight functions here just to because of to wait when computation could be done and then measure the performance. This is specific functions to measure execution time extracted as part of MKL. And of course, here we could use exception handling exceptions to try to take the exceptions in the case of something will go wrong. And that's all. And we compare the execution to run this code on CPU side and on GPU side. Running this code at the very beginning, sorry, I forget my where I put this JSM, just moment. Okay. And I built both of these examples here. Here just I will show some kind of make files. It's actually, of course, not make files, but this is kind of build script. But you might see that building this code requires significantly different compared with what we have with C or C interfaces. For example, here when we build C code, here is the link line we use typically. But with DPC++ interfaces, of course, we use DPC++ driver here. Then we used has to be linked against SQL libraries, Intel MPI, TBB threading. By the way, TBB threading building runtime used by in DPC++ in DPC++ interfaces by the default. And we could link against OpenCL libraries as well. Okay, and then let me just show how it could run driver with USM. For example, this is input numbers, and this just some additional parameters. That's mean this shared memory matrix multiplication would run on CPU part, and they will perform as 164 gigaflops. In this case, we could easily to check if what exactly has been run by adding MKL verbose mode and then repeats this call once again. And you might see that MKL has been run many times, and the shortest time could be reported and reported to compute the output performance. We could see that the code has been running as the AVX512 code path because of this host CPU is AVX2 code path, and Linux frequency ILP64 and interfaces and TBB threading runtime has been used in these cases. Yes, and then let's run this code on GPU part. On GPU part, setting different numbers, then CPU GPU content could be run, and we could see there are no variables in this case. This limitation could be fixed very soon. The next update could support MKL verbose when the code could be running on GPU part, and we could see that the performance would be 94 gigaflops. Of course, much less than running code on GPU side, but in this case, host much more power than this very not very big GPU card as well. At the latest discrete cards, if you run, we could see very significant performance differences between running this code on GPU and CPU part many times, but it's just separate topics for presentation. And if you need some NDA session, if you would like to see these results, okay, just a moment. Thanks, Dmitry. Sparsina GPU MKL. Yes, we support sparse BLAS on GPU, of course, but not all available sparse BLAS routines. But most important routines available there, like sparse matrix by dense vectors, sparse matrix by sparse matrix, and save the output results into sparse representation or dense representation, and some another. And some part of functions available to run on with offload mode as well. But our intention here we just want to hear which functions you want to see else at this from these routines. Georg, if you just write now your request, we will consider these features into the next version updates, etc. Let us feedback you. Yeah. Did I answer on this question? Okay. And let me run this code. For example, buffer interfaces with the same problem size. Running on GPU side, offloading this code to implicitly offloading this code, and you might see the performance results are pretty similar. It just very expected results. And that's all with, and go to the offload. Just I prepared another examples. Offload C examples. I prepared another examples where the code looks very similar. Once again, the code modification, the code is the same. Like we have to run this code on CPU side, and we only added a couple of lines, here to run and to build to make this code offloading on GPU side. And I already compile this code here, and let me show that how it. And once again, with the same problem size, and how TGM could upload to the local GPU, to the current GPU, and compare with how this code would be executed on CPU side. I measured the total time including execution on execution. Here, the first line means execution time on CPU side, on the host, and the second line total offload time, including offloading all input arrays to the GPU, execution layer, and back output series C arrays back to the host, and make some comparison between what we computed on CPU and on GPU paths. That's, I think, all I would like to show today. Not today, regarding to offloading. Just let me back to my files, and I would like to share. I would like to spend some 10 minutes, 15 minutes left to speak about another libraries we have. This is just integrative performance primitive, which provides developers a very wide set of image signal data processing, and as well as cryptography algorithms. And the total number of supported API exceeded several thousands. It's a very rich, set of different functions. The same as MKL. This is cross-platform API, Windows, Linux, Mac OS, and optimized as well as MKL. And for some functionality like filtering, app reused MKL optimization as a backend. And and here we have what we have with IPP today. Today we have image processing. We have image processing domain, which contains color conversion function from one format to another format, very rich functions with different layout, with different number of channels, and many others, and with different color scheme, and wide set of computer vision functions, which highly used in OpenCV library, and rich set of image processing library. This is under one umbrella, which called image domain. Signal processing as well, the same, mostly the same like we have an image processing, but related to one-dimensional calls as well. And this is compressions, many algorithms we have. IPP has here zlib, LZ4, and many others, and cryptography algorithms. Our plan today, all of these functions, all of this API are C interfaces, so-called classical C interfaces, available for and optimized for all classical Intel architecture. But we are on the very first stage to port this code on DPC++ to run this code on GPU part as well, the same as we already did with MKL and with another performance libraries. We just published oneAPI image processing and signal processing, signal processing, and data compression specification available here. You may be just to check how the future interfaces could be done. We are planning to start beta program very soon, and all of this functionality could be, not all, but some part of this functionality could be available, could be released this year. And if some of you interested to see some of specific functionality from image signal processing or data compression, please let us know. We will add this function to our plan. Regarding to cryptography, it would not be this functionality. We are not planning to port on GPU side, at least at this moment. We see no benefits to run this code on GPU side today. And another point, just I think it's everything we have. And for today, regarding to IPP. And the third library we have is just Vandal, formerly known as Intel Data Analytic Acceleration Library. The library provides set of optimized building block for all data analytic steps. You might see here just for pre-processing, transformation, analysis, modeling, and decision making. From take using only DPC++ interfaces libraries, you could take the numbers, train these numbers, create some model, and to offload this model to the edge devices and execute this model or at the edge devices. To be shortly, DAL suggests very wide set of API. DAL supports C++ interfaces, Java and Python interfaces, as well. And you might see just DAL suggests supports different so-called offline streaming distribution usage models to work with input data. Offline means if you at the runtime all needed data are available at the runtime, and you need to take this data, to proceed with this data, and to create some model. If data changed or if data coming to your devices from time to time, you need to proceed with each pieces of this data and edit and piece by piece cases. And of course, some of supported algorithms are working into the distributed mode by using MPI by using clustering mode. And this is just what we have regarding to machine learning interfaces. Here we have linear regression, decision forum, gradient boosting algorithms, logistic regression, KNN algorithms are available, dense B-scan, etc., are available to run on GPU side, on Intel GPU side as well, the same as we have with MKL. All others just to run on CPU side. And by the way, gradient boosting here, just it's not this functionality. Intel DAO team contribute to the original implementation of gradient boosting, and this optimization, our optimization, available from gradient boosting GitHub. Just and the last topics I have here, just to show you that data transformation and analysis functionality, also part of this functionality has been ported to the GPU side. Not all, but from our understanding, most important, like principal component analysis, gradient decision functionality, and all some kind of basic statistic functionality available to run on GPU side. All others, just we are only planning to port some of them. In other, just we are thinking about how to do this. If you like, if you require to extend this functionality, please contact us. Please contact with Edmund, and just he will to let them know what you like to do, what you like to see, and we will add this functionality in the future. And the last free files, just I added all available resources to take all needed information for your reference. I think I finished my very short presentation regarding to these topics. Thank you. Any questions so far?